In this work, we present a one-shot mixed precision searching method. Our first contribution is that we theoretically derive an earlier empirically found state-of-the-art searching methods. We do this by adding one-hot gates to a supernet, which enable quantization of weights and inputs. In addition, we propose a generic approach to model hardware constraints by a Boltzmann distribution. Our second contribution is that we propose to augment a supernet with a bitwidth prediction model that allows searching for Pareto front models in no one time. To do so, we parameterize one-hot gates by some function of a hardware penalty. For large models, the proposed method is 5 times more efficient than existing methods. Bitwidth probability model allows to avoid coadaptation of weights, which results in a high correlation score. Found models are of a similar quality with other algorithms, but have a richer set of bitwidth combinations. We attribute this to the structure imposed by the bitwidth probability model. We use quantization as our main tool for reducing latency and power consumption during inference. We quantize both weights and activations. We quantize them in 2 bits, 4 bits, or 8 bits. We use uniform grid, and we use quantization-aware training. So imagine that we want to speed up UNet. Some hardware already supports mixed precision operations. So we can suppose that maybe some middle layers should be quantized in lower bitwidths and the outer layers should have a larger bitwidths. And this may work in principle, but to be generic, we should be able to find bitwidths of each tensor individually. And you can imagine that this results in a quite large searching space. Furthermore, for practical reasons, it is more convenient to find multiple Pareto front models. So for example, in this plot, each green dot corresponds to a Pareto front model, and each of these models is optimal with respect to the trade-off between bit operations and some metric, which is PSNR in this particular case. There are one-stage algorithms which require multiple restarts, each restart to find a new such Pareto front model. And there are two-stage algorithms which first train a supernet, which is done once, and then they do an additional search over this trained supernet. So for example, SPOS uses evolutionary search, which is rather slow, or BitMixer and FNCube use some heuristics. But can we do better? Yeah, our answer is yes. So here you can see a supernet convolution block where we place one hot gates Z in front of each quantizer. And when the gate is open, it means that the tensor passes through the gate to the quantizer, and then the convolution is performed. And the task is to find the posterior probability distribution PZ given data of a gate being open. We cannot calculate it using the bias rule, but we can approximate it using some variational distribution Q pi of Z by minimizing the KL divergence between these two probability distributions. And such minimization boils down to maximizing elbow. So after we do math, we arrive to this equation, which is composed of 3 parts. The first part is a task loss, for example, some classification or regression loss. The second part is a hardware penalty term, where PKB is a prior distribution for a gate being open, and eta in this equation is a hardware penalty. So it controls how easily the gate is opened or closed, because it accounts for H, which is the amount of resources, for example, bit operations required for layer K to be quantized in bitwidth B. And the final term is an entropy. So here you can see the comparison with EdMIPS algorithm, everything else being equal. And what's more interesting about our approach is that it generalizes both to DNAS and EdMIPS. So for example, when we use Q pi of Z as a concrete distribution, we obtain DNAS, and when we use softmax function as a proxy for gate probabilities, we obtain EdMIPS. And there are also some other minor differences, like for example, both EdMIPS and DNAS do not use entropy term. But now the question is how to find Pareto architectures at once. And we propose to parameterize gates by some function f of eta. This function is parameterized by its own parameters theta. So now eta participates in the loss function and also controls the gates. Here you can see a graphical model of this process, and the equation below is the loss for our one-shot mixed precision search. In green part is the elbow loss that you saw previously in previous slides, and here we take expectation over eta, which is sampled from some log uniform distribution, and we also add a kernel similarity loss, which helps to avoid Bitwidth model collapse. So here is an intuition behind the Bitwidth probability model. What it learns is to output a Bitwidth depending on the input hardware penalty eta, and we do this for each tensor in the network. So interestingly, the correlation between the child and standalone model is also high. A child model is a model that is sampled from a supernet and is evaluated on a validation dataset without fine-tuning. And standalone model is the one that we further fine-tune, possibly on some different, maybe larger dataset. Yellow color in this plot corresponds to the model with the highest bit operations. So you can imagine that this yellow dot should achieve the highest child accuracy and the highest standalone accuracy. And this is only valid for our one-shot MPS methods. For more details about this plot, please refer the paper. So we can say in conclusion that Bitwidth probability model allows to avoid coadaptation of weights, which results in a high correlation score here. So we theoretically derived two new searching methods, VIMPS and one-shot MPS. We showed that the Bitwidth probability model allows for a straightforward Pareto front architecture selection. And we show that this Bitwidth probability model imposes some structure on the selected architectures, due to which we find a richer set of Bitwidth combinations and achieve a very high Kendall's-Tau correlation score. So to conclude, I want to thank you for your attention, and if you have any questions, please feel free to email me.